Hello, I'm Gheehyun. I'll be talking about probability, expected values, and gamblers. So first, thank you for inviting me to this forum, and it's a great honor. Please stop me if you don't understand anything I'm talking about, because it's kind of important that I talk clearly here. And if you have anything that you'd like to share while I'm talking, please just shout out. And I just learned that I'm very bad at like reading the chat. So if I miss something, please let me know.
Please also feel free to send questions for Gheehyun to staff with private messages, because
yes.
it is very hard to read the chat when you're presenting.
Yeah, I learned that last time. So I'm not really sure how much probability you know. So let's first review some by going through some questions. So what is the probability of throwing a 6 on a fair six-sided die?
1/6.
1/6. So there are 6 possible outcomes, and they are all, the probability of them showing up are the same, so it should be 1/6. And maybe a more interesting question might be something like, what if you throw 2 dice? So you take the sum of the 2 numbers that show up, and I want to ask, what the probability of throwing a 6 is. So for instance, you could throw a 1 and a 5 or 2 and a 4 and so on. Any ideas?
One on 36.
Oh, nice. So there are in total 36 different outcomes, and all of them have the same probability of showing up. And so among these outcomes, there are 5 cases where the sum equals 6, because you could throw 1 and a 5, 2 and a 4, 3 and a 3, 4 and a 2, or 5 and a 1. So there are 5 outcomes, and you have to divide it by 36, which gives 5/36. Okay, so maybe we could move on to expectation. So what is the expected value of a die? A fair 6-sided die? So the numbers that you could throw are 1, 2, 3, 4, 5, and 6, and they come up with probability 1/6. So it should be 1/6. So there should be 1, which is the value, and this comes up with probability 1/6. So, and then 2 shows up with probability 1/6, and you sum these all of these up, which becomes, yes, thank you, 3.5. So is everyone happy with this? So we could probably move on. What about the expectation of the sum of the values of 10 dice? Okay, so someone suggested that it is 35. So why is it so, Mark?
I mean, so you would think that since the expected value of rolling 1 dice is 3.5, when you roll 10 dice, each dice has an expected value of 3.5. And since these dice are presumably untampered with and they therefore have the same expected value, all you do is you add these values together because they're independent of each other. Because like how you roll one dice doesn't affect the way that the other dice will roll, which means that you essentially add all of them together and you get 35.
Thank you, Mark. So there are 2 points that Mark made. One is that the expected values of each dice is 3.5 and they add up. So you did something like 3.5, but there are 10 dice, so you add them all up, which gives 35. And you also mentioned something about independence. So maybe I should talk about this a bit. So I think a good point is that here actually independence doesn't really matter, because expected values add up. I mean, they always add up, regardless of whether your random variables are independent. So I'll demonstrate that with an example afterwards, but maybe I should elaborate on this adding up part. So if you're familiar with a more abstract way of looking at probability, you would have heard about these kind of random variables. So asking what the expected value of rolling a die is basically asking, so I have this random variable, which is the outcome of a dice roll, and then let's denote it by x. And then I basically want to ask what the expected value of x is. And when I'm asking what the expected value of the sum of 10 dice is, we have 10 random variables, x1 up to x10, which is the outcome of so x1 is the outcome of the first dice throw, and x10 is the outcome of the 10th die throw. So now I'm asking what the expected value of x1 plus up to x10 is. I'm claiming that you could basically the expected value of the sum of some random variables is just the sum of the expected value of each of these. So I'm claiming that this holds. So maybe this is a bit too abstract, but the point is that if you want to compute the expectation of the sum of a few stuff, then you could basically just first calculate the expected value of each of these and then add them all up. So I'll demonstrate this by some other example where these random variables are not independent. So here, well, you throw a die, and then if you throw 1, 2, or 3, then you throw the same die again. Otherwise, so if you have thrown 4, 5, or 6, then throw a coin, and you get 7 if you throw heads, and 0 if you throw tails. Okay, so maybe I should draw this. So you throw a die, and if you've thrown 1, 2, or 3, you throw it again. If you've thrown 4, 5, or 6, then you throw a coin, and you multiply this by 7. So this will be 0 or 7. So can someone tell me what the expected value of this is? Yes, this is 3.5, as Joseph mentioned. So this is 3.5 because it's 7 with 1/2 probability and is 0 with probability 1/2. And these are also 3.5. So we could think of this as, so we're adding these two numbers up. And we will think of this as, well, we're adding the expectation of this, expected value of this, and then we're adding the expected value of this. Well, But here, regardless of whether you've thrown a 3 or a 4 on the first throw, the expected value of the second throw is 3.5. And we also know that the expected value of the first throw is also 3.5. So you just add them all up. So the expected value is 7. Does this make sense? Is everyone kind of happy, or should I explain a bit more? Or maybe this is a bit too simple. Any questions? I think it's kind of important to understand this very well because I'm gonna utilize this kind of facts a lot throughout this talk. So the point here is that it doesn't really matter whether these two events are independent, because see, if you've thrown a 3, so let's consider the two cases where you've thrown a 3 or where you've thrown a 4. Then the probability of you throwing a 7 on the second turn is different, right? Because in this case, it'll be basically, it'll be 0, and in this case, it'll be 1/2. So while these two events, 1 and 2, are not independent bits, the expected values add up. So I'll move on. So maybe another good point is the following. So I want to sort of simulate a kind of a stock exchange. So there will be stock prices. So let's say that the price starts at 10. So this will be time, and this will be price. So every hour, let's say, you toss a coin. Heads. If you toss a head, then then the price increases by 1. If you throw a tail, then price decreases by 1. So for instance, if you've thrown a head, then the price will go up to 11 and so on. Let's say that you finish at this stock exchange terminates at the 10th hour. Now, at each point of time, you could sort of choose to buy or sell one sort of stock. So for instance, if you've chosen to buy one stock at hour 0 at 10, so you've bought one here, and let's say that you tossed a head and you decided to sell one at hour 1. So then you'll make a net profit of 1. Well, let's say $1. And the point I want to make here is that because of linearity of expectation, which means that expected values just add up, whatever you do does not affect the expected value of your net profit. Because, so for instance, if I've decided to buy at hour 0 or sell at hour 0, I mean, so let's say that we've bought a stock at hour 0, then because the price moves like this, we can see that, for instance, at hour 1, our net profit would have expected value 0, because it'll be 1 with probability 1/2 and -1 with probability 1/2. So they add up to 0. And that's the same no matter what you do, given that it finishes at hour 10. Is this kind of clear as well? I hope that was clear, but we might be able to move on because I sort of have different themes. So okay, maybe I should skip this example because it's maybe a bit complicated, but I wanted to make the point that I really wanted to stress the fact that linearity of expectation does not have to do anything with your random variables being independent. I guess I've done that already. So let's move on to the problems. Okay, so let's say that you throw a die until you throw a 6. You want to know the expected number of throws that you've made. Does anyone have any suggestions on how we should think about this or how we should approach this question? So someone said is 6. Maybe you could explain why you thought so.
There's a probability of like 1/6.
Sorry, I think your microphone is a bit maybe too far away. I can't hear you well. Or maybe you could type it and I could read it. Yes, so there is a possibility of 1/6 throwing a 6. How does that relate to the expected number of throws? So I'm not sure whether I've understood your arguments well. So the argument that you've given is something like throwing a 6 has probability 1/6. So we have to throw it 6 times. Well, so what's the probability of throwing a 6 if we've thrown a die 6 times? But so maybe let's talk about coins. So wait, I'm not sure how to so if you've thrown the die 6 times, then what's the probability of you throwing a 6 in at least one of those 6 throws? So Joseph said that so I think I think 3 different people said that 3 different people's argument all basically boil down to so each number has probability 1/6 of showing up. So if you throw it 6 times, then that number will show up. Is this kind of the argument that you came up with?
Yes. I'm not sure.
So well, let's do a sanity check. So let's say that we've thrown a die 6 times. So maybe so the point I want. So somebody talked about the geometric distribution, which is correct. So this, I'm talking about the geometric distribution here. And from what I could tell, I don't think that, well, you should at least explain a bit more, because okay, so maybe a different example would be something like, okay, you throw a coin repeatedly until you throw 2 hits in a row. And what will be the probability of, what will be the expected number of throws here? And why is it 4? Sorry. So I think the usual solution is something like this. So let's consider, so the expected value of a event is something like, a random variable is something like, so you have to sum up all the possible values multiplied by the probability of it occurring. So you will have thrown exactly once with probability 1/6, because you'll have to get a 6 on your first throw. And then you'll have to throw it twice to get a 6. And that'll have probability 5/6 times 1/6. So that is, so on your first throw, you shouldn't have thrown a 6. And then on your second throw, you have to throw a 6. So that should be 5/6 times 1/6. And then you apply the same logic. And you basically have to add all this up. Does it make sense? So it's not that simple to calculate this. And the usual way of doing this is you multiply 5/6 to x, and this will become like this, and you subtract these, which will give so you will have x equals maybe I should write it like this. So you do the same thing here. So you say, well, oops. And you subtract this again. So x equals 6. Does this make sense? I think the key thing to understand here is how this formula showed up, and maybe the following the calculation is not that important. It's just to demonstrate that it's not trivial. So I hope this part makes sense, because so the expected value is basically the sum of each possible value times the probability of it occurring. So 1 will occur with probability 1/6, 2 will occur with probability this, and 3 will occur with probability this, and so on. So, well, the answer is 6, as you've mentioned, but I'm not really convinced by the argument that you've made. And I want to present an argument that is very similar, but which can be justified. So it's by the solution utilizes gamblers and how gamblers can't make money in a zero-sum game, sort of. So let's say that so a toy example might be so I am a gambler and I pay $1 to play the following game. Maybe this is not a toy example. So I pay $1 to play a game, and I get $6 if I throw a 6. So I throw a die again here, and I don't get anything otherwise. Well, what is the expected outcome of this game? Well, it is 0, because, well, I will get $5. My net outcome will be +5 with probability 1/6, and -1 with probability 5/6. So adding these will give me 0. So the expected outcome of this game for me is 0. Well, now I will claim that no matter how many times I play this game, and regardless of when I would like to stop this game, given that I can't see the future or something, the expected outcome, the expected net profits will be 0. Well, I guess this kind of makes sense, because if you're playing a game in a casino, for instance, I mean, your expected outcome, expected profits will not depend on when you'd like to stop. Maybe this is a bit counterintuitive, but so if you use this fact, then we could see that the expected number of throws is exactly 6, just as follows. So I always pay $1 to play a game, and let's say that I play this game until I throw a 6. Expected profit is 0 regardless of when they decide to. So the idea is play this game until they throw a 6. So then you will have paid $1 times the expected number of throws and will have received exactly $6 because you play this game until you throw a 6 and then you stop. So we know that your expected profit is 0 no matter what. So these two numbers should be equal. So you get that this is 6. I hope we're happy with this. So, well, here maybe this is a harder way to do this, but I'll show you that this kind of argument can be utilized in different situations where it's more complicated to work out the solution otherwise in a different way. So the point I made is that the gambler sort of can't gain more profit or can't change the expected profit by cleverly deciding when to stop. So, well, but maybe you might disagree because, for instance, if you have a stock, just like this example, and let's say that you first buy a stock at when the price is $10, and you decide to sell it when it reaches $11 and don't care about when it reaches $11. It might reach $11 when it like a year afterwards, but you don't care about it and you just wait for it to reach $11 because you think maybe it will. So, well, this is a strategy and you will almost surely gain $1 from this strategy. But the point is that you might have to wait a lot. So you might have to wait sort of infinitely. And so this point actually has a big asterisk. So I should have said that a gambler cannot make money by cleverly choosing when to stop, given that they are not allowed to, for instance, if they are not allowed to wait indefinitely long. So you should have some kind of finiteness. So you either don't have finite time, you either don't have infinite time, so you can't wait indefinitely, or you have bounded money. So you can't you can't have more than a specified amount of money, and you can't, for instance, go bankrupt. So these are the conditions, well, sufficient conditions. And another sanity check that we have to do is that the game you're playing, the expected outcome of, for instance, the nth game does not depend on how much money you've made until the n-1 round. So, well, the game could sort of change depending on how much money you've made or the action you've made up to that point, but the expected value of the game should not change. So for instance, if you've already made $10 until today, then, well, you've already made $10, and the expected outcome starting from tomorrow onwards should not change because you already made $10. So the game that I'm applying this point to should satisfy these conditions. So I just realized I'm running short on time, so maybe I should talk about this problem instead. So maybe this is a bit more interesting. So you throw a coin until you throw HHTTHTH in a row, and you want to find out the expected number of tosses. So this is more complicated than before, and you can't say, well, there are 1, 2, 3, 4, 5, 6, 7. And the length is 7, so it should be 2 to the 7, which is 128. The answer is not 128. And here you could also calculate the expected number of tosses by utilizing this gambler idea. So here, actually, the nice idea that you have to come up with is coming up with many gamblers instead of one. So a gambler does the following. So a gambler starts by betting $1, and then they get none. So on the first round, get none. So receive double the amount if H comes up. And on the second round, they bet whatever they have. So basically, if they've lost on the first round, then they can't join the second round. But if they've won the first round, then they bet $2, and they will receive double the amount if and only if H comes up. So on the third round, they do the same thing. And here, instead of getting receiving double if H shows up, you receive double the amount you've bet if T shows up. So I guess I haven't explained my point. But the point is that on the fourth round, it's the same but with tails, and on the fifth, it's the same but with heads, and then tails, and then heads. So the point is that this gambler will last 7 rounds if and only if HHTTHTH shows up in a row. Lasts 7 rounds if and only if the retoss HHTTHTH. Well, I will use this to calculate the expected number of tosses. So here in this problem, well, it's a bit different from what I've just explained, because you throw a coin indefinitely until you throw this in a row. So let's say maybe you've thrown T, 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 H, T, H, T, and so on. But now the idea is that you have, so for before each throw, a gambler joins. So before the first throw, a gambler joins. So this gambler, let's say this gambler is A, then A will join and see that, and bet $1 and see that you've thrown a tail, and then they will lose all of their money. And then B will join here, and then, well, they will lose all of their money. And C will join here, and they will lose all of their money as well. But here D will join, and they will bet $1, and they will receive double of that. So they will end up with $2 after this throw. And here E will join, but D will also bet $2, and they will be on the second round, and they will actually lose all of their $2 because you thrown a tail, and E will also lose all of their $1 because you've thrown a tail. And then F will join, and so on. So the point is that, so after you've thrown H, H, T, T, H, T, H in a row for the first time, well, the gambler that started at this point, before this point, will all have $0. But the gambler that started at this point will have 2 to the $7, which is 128. And the gamblers that started at these points will have none. And the gambler that started at this point will have $2. So now in order to calculate the number of throws the expected number of tosses, you just say that, well, you've paid all of these gamblers 130 in total, but they've paid you $1 times the expected number of tosses. And since you know that the gamblers cannot change their expected value of their net profit by cleverly choosing when to stop, you basically know that the expected number of tosses is 2 to the 7 plus 2, which is 130. So I think time is up. If I have more time, I could do some more examples.
We still have around 5 to 10 minutes.
Oh, I see. So
Yeah.
maybe I should do another example. So, okay, so let us recall this kind of random walk we did. So this kind of thing is called a random walk. So you start at 0, for instance, here, and at each point, so for instance, every second you toss a coin, and if you throw a head, then you move +1. If you throw a tail, then you move -1. So, and let's say that you have these two numbers, -a and b. Let's say, for instance, it's -3 and 4. And you stop when you hit one of these. And I want to know what the probability of hitting 4 is. So it's basically asking what the probability of hitting 4 before hitting -3 is. And in order to solve this question, we could also do brute force. So by this I mean, so you'll introduce some variables. So let's say this is x0. So x0 will be the probability of hitting b if you've started at 0, and x will be the same thing, but if you start at 1 and so on. Then you could come up with some equations. So x0 will be 1/2 times. So let's say, so since you throw a head with probability 1/2, so it'll be 1/2 times x1 plus 1/2 times x -1, and you get a sort of system of linear equations, and you could solve this because, for instance, x4 is 1 and x -3 is 0. So this is the brute force way, but this is not very maybe interesting. So a simpler way might be introducing gamblers in this case. So let's say that you are a gambler, and you pay $1 to play the same game that we played. So you pay $1 and you get $2 if I throw a head, and you don't get anything if otherwise. So then the expected value is 0. Get 2 if heads, 0 if tails, then expected value is 0. So now let's say you stopped if your net profit is $4 or -$3. and so here, you know that the expected value of your net profit is 0, and you could basically use this fact to calculate the probability of hitting 4. Because let's say that P is the probability of hitting 4. Then 1 minus P is the probability of hitting -3. And now the expected value of the net profit is basically 4 times P minus 3 times 1 minus P, which is 0. So we know that 7 times P equals 3. So P is 3/7. So this answer here, so in the general case, this will be A over A plus B, if you do the same calculations. So to end my talk, I'd like to mention that this actually is a mathematical thing. Well, it boils down to linearity of expectation, but there is maybe a fancier name called martingales, and this kind of gamer strategy that I've told you of solving these kind of problems is basically using the optional stopping theorem of martingales. So you could maybe check that out. And I think one point that you might want to take home from this talk is that if you're gambling or if you're sort of trading in a stock exchange, then a good point is that you cannot make money just by stopping at the right time. So it means that each of your trades has to have positive expected value to make money. And just by doing some random trades and hoping your stock will rise, or hoping that you can sort of exit at the right time by stopping cleverly is not a good idea, because it's mathematically impossible. So I guess this is a good time to end my talk. Thank you for listening.